Determine whether the graph of the polar equation is symmetric with respect to the x, y, or origin. So what we're going to do for this problem is we're actually going to graph it. Now, the book does it a little differently. They just kind of plug in a negative and say, oh, it works. So again, they have to understand the answer already to even work this problem out. So to me, that's not really even doing anything, essentially. So what we're going to do is we're going to actually just graph this one, because it's good to learn how to graph anyways. This is a perfect time for it. So we need a polar grid first. There we go. And we're also going to need an r theta table, because we're going to have to do a bunch of values here. I think we're going to need a lot of values here, so we're going to use another table along with this one. We're going to need two of them. So we're going to start at 0, so 0 degrees. And I'm not going to put the degree symbol in there. It's going to take up some space. And I'm just going to go I'd like to go every pi fourths. But if you look at where we're at here, this is 2 theta. So I'm going to go every 15 degrees, because if I put a 15 degrees in here, when I double it, it's going to be 30. And then when I put a 30 degrees in there, it's going to be a 60 degrees. So I'm going to take that approach with this one. I'm going to do every 15 degrees. So actually, I'm probably going to need a third table. So I'll get 0, 15, 30, 45, and I'm going to go all the way around to 2 pi. Yep, so almost 3 complete tables I needed here. So now I'm just going to fill in the r here. So what I mean by that is, so for the first one, it's 0 degrees. So if I was going to plug that in, this would be 3 times the sine of 2 times 0, and that's the sine of 0 is actually going to be 0. So 0 times 3 is 0. So when I plug in 0 for theta, I get 0 for r. So I'm just going to run through these this way. And again, when I plug in 15 degrees and get the sine of 30 here, after I times it by 2, I only want the decimal approximations of these because I'm going to have to graph them. So make sure you do the decimal approximations, and make sure you have your calculator in the right mode with this as well. And actually, radians might be better if you're using a CAS, because in general, that's what they use for those. You can change your modes, but a lot of times they're already set in radians. So if you know 15 degrees is just pi 12s, you can go every pi 12s. So really just pi 12s, 2 pi 12s, 3 pi 12s, and you can just kind of take that approach with those if you choose. So anyway, so just run through the table and just fill in all the values. Again, make sure you're using decimal approximations here because we're graphing them. So there's all of our values. So now what we're going to do is we're just going to graph these. So the first one is 0, 0, so that's there. And then what we're going to do here is, I wanted to actually relabel my my other values for my radius here. So I'm going to say every 2 notches here is going to be 1 here. So this is going to be 1, 2 here, and 3 there. So it's every 2, because it'll make our graph look a lot nicer the further we can go out and spread our points out. So now the next point then is going to be 15 degrees, 1.5. So if you look at the 15 degrees, that would be here, and we're going to go out 1.5. So here is 1, there's 2, so 1.5 is going to be there. So it's going to be 1.5 is going to put me there. So there's my next point. Now at 30 degrees, it's 2.598. So it's slightly past 2.5. Okay, and the next one at 45 degrees, it's going to be 3. Oops. And at 60 degrees, it's 2.59 again. So it's going to be just above there again. So we're going to start seeing that symmetry. And at 75 degrees, it's going to be 1.5. So here's 75, and 1.5 is going to be there. Oops, yep, I didn't go quite right. I went too far. So 1.5 is going to be there. Yeah, went too high the first time. All right, and then the next one's going to be back at 0. So that's back here again. Okay, and then from there, we're going to go to, at 90 degrees, it's going to be 0. Yep, that's back there. Okay, and then at 105 degrees, at 105 degrees, it's going to be negative 1.5. So keep in mind, 105 is here, but since it's negative, it's going to shoot out the other side here. So it's going to come out this way, and that's going to be the 1.5. So it's going to come out this way till about there. So then at 120 degrees, which is here, it's going to be negative 2.598. So it's going to come out the other side. It's going to be a little bit past 2.5. Okay, and that's going to be there. And then the next one's going to be negative 3 at 135 degrees. So again, that's going to shoot through the other side, and that's going to be there. And then the next one then is going to be at 150 degrees, and that's going to be a negative 2.59 again, so that's going to be there. And then at 165, it's going to be 1.5 again. And then it's going to go back to 0, so it's going to go back there. Okay, now the next point then is going to be at 180, it's going to be 0 again. Yep. So then from there, after 180, it's going to be 195, and at 195 degrees, it's going to be 1.5. So that'll be there. So then the next one then is going to be 210. It's going to be 2.59. And then at 225 degrees, it's going to be 3. And then at 240 degrees, it's going to be 2.59 again. And then at 255 degrees, it's going to be 1.5. So it's going to put it there. And then at 270 degrees, it's going to be back at 0 again. So then at 285, which is here, it's going to be negative again. So at 285, it's going to be negative 1.5. So it's going to be there. And then at 300 degrees, it's also going to be negative, and that's going to be a negative 2.59. And then at 315, if I shoot it through the other side, that's going to be at negative 3 there. And then at 330 degrees, it's going to be negative 2.59 again. I'll make it a little bit tighter there, okay? And then at 345 degrees, it's going to be 1.5 again, negative though, so it's going to put it through the other side. And then at 360 degrees, I'm back at 0. Okay, so now I'm going to just connect the dots from where I started. So now remember, I started at 0, so I'm coming around this way, coming up there, coming back around, hit 0 again. Then I went over in this quadrant here, went around, went back to 0 again, and then I'm coming over here now, went back around, went back to 0 again. Now I'm cutting around here, went back to 0. So that's our graph there. And we also have a direction on this graph, and it would be in that direction there. So now let's talk about this idea of symmetry here. Okay, so do you think I have symmetry across the x? So when I talk about this idea of symmetry, if I draw half of my graph, I can see that I can draw the other half the same way, going the other way. So my symmetry here would be across the y. Now I don't have it across the x, even though if you think about just drawing this line and flopping it over, it's not that simple. If I think about the mapping of this, I have to be able to create the full picture of that side in order to map it across the other side to talk about symmetry. So the symmetry I would have here would only be across the y, which means it would come across this way. So that would be the only symmetry I would have for this one. So it would be across the y-axis. So the other nice thing about this is I wanted to show you guys how to graph in polar coordinates, just in case you had forgotten about this. So anyways, there's a lot of this that's done when you get to Calc 3. Not a lot, but you'll see it here and there. And we're definitely going to have some integrals of these also. So this is definitely something worthwhile. So there's our answer for this one, and the answer would be the y-axis. But again, I just wanted to graph it so you understood how to graph. I wouldn't have had to do it for this problem. The problem just says, oh, just plug in negative and you can pull the negative out, done. But you have to understand that it's symmetric with the y anyways in order to think about it that way. So you're just using those cofunction identities if you want to go back to that. But also remember, with this problem here, we do have an orientation as well. And this is what we call a rose. So this is a rose here with 4 petals. And it's interesting because with this 2 theta here, that 2 theta created 4 petals, which I thought was interesting. But anyways, there it is.